if I have a boundary between two different materials, and let's say the bottom material is has an index of refraction of 1.5, and the top material has an index of refraction of 1.2. Doesn't matter what these materials are. If I want to shine a light through here and have any hope of total internal reflection taking place, which way do I got to shine it? Down or up? I got to shine it up, right? Because if total internal reflection is going to occur, there's two conditions that must be met. One of them is that the light must be going from the medium with the high index of refraction to low index of refraction. No exceptions to that. You can't get it going from low to high. You sometimes get it going from high to low. So let's shine a beam of light here. That's got a fairly small angle of incidence, right? Theta 1, fairly small value right there. That ray of light, as it's going from high index to low index, it's going to bend which way? If n goes down, then theta goes, n goes down, and it has, right? We're going from 1.5 to 1.2, then theta is going to do what? Theta is going to go up, right? So that's going to bend away from the normal line. Theta 2 will be bigger than theta 1. That is, assuming that we haven't exceeded the critical angle. If we've exceeded the critical angle, then we don't get refraction, right? And all of this is for naught. But assuming that refraction takes place, then theta 2 will be bigger than theta 1, as will v. v2 will be bigger than v1, as will lambda. Lambda 2 will be bigger than lambda 1. As n goes down, then v goes up, lambda goes up, and theta goes up. If I increase the angle of incidence to this point that we call the critical angle, what happens to that ray of light? What happens to that red ray now? Yep. Yeah, it just kind of skips around the boundary there. What's the angle of refraction now? 90 degrees. So if I want to solve for this critical angle, then what I'm going to do is use Snell's law, say sine theta 1 over sine theta 2 equals usually n2 over n1, although if you're given the speeds, you could use v1 over v2 or lambda 1 over lambda 2. I'm going to replace theta 1 with theta c, and I'm going to replace theta 2 with what? What's the value of theta 2 at the critical angle? Yep, 90 degrees. And what's sine 90? 1. So the equation becomes, every single time you're trying to find the critical angle, sine theta c is equal to n2 over n1. Or theta c is equal to the inverse sine of n2 over n1. And the beauty of this, mathematically, is if you mix up n1 and n2, and that's really the only thing that can go wrong on this. If you mix those two up, your calculator is going to give you an error, tell you made a mistake, tell you to try again. Mix it and switch it around the other way. All right. If we have a small difference in index of refraction like we have right here, what would you expect the critical angle to be? A small value or a big value? Here, 1.2 and 1.5 aren't all that far apart. We should expect the critical angle here to be fairly what? No, it's actually going to be fairly big. When you have a small difference in index of refraction, you have a big critical angle, right? Think of it as n goes down, theta goes up, right? Small difference in index of refraction, big critical angle. And that's why diamond and air have a really small critical angle of 24 degrees, because they have such a big difference in index of refraction, 1 and 2.4. Does that make sense? All right, so if you want reflection to occur, then what you want to do is probably have two media that are very different from one another with different indices of refraction. If you don't want it to occur, then you want the index of refraction of those two materials to be fairly similar. All right, we had 3 questions that you worked on yesterday. Were there any issues with these 3 questions? You want to go over any of them? They're all the same, right? They're all the same. Sometimes you get a question with some context, like here's what we call an optical fiber. Do you guys know what a fiber? You ever heard of fiber optics? Yeah, what is fiber optics? What's an optical fiber? It's a little glass wire that carries visible light, and that will, with that visible light, carry information on it, encoded information. And it's really, really efficient. The bandwidth of it is much, much higher than electrical wires, than copper wires that carry information by moving electrons, by pumping electrons through it. It's much more efficient, carries much more bandwidth, and it has much less, normally at least, much less signal loss along that wire. The way it works is that you get a ray of light here, a ray of light that's carrying information, and it strikes the boundary between the glass, this is glass, right, and the air. Assuming that theta 1 is bigger than the critical angle, then it's going to bounce off. And assuming that one is bigger than the critical angle, then it's going to bounce off, and so on and so on and so on. So that beam of light and every other beam of light that's going in this fiber optic cable makes it from one end all the way down to the other end with virtually no signal loss. Does that make sense? Now, the problem is, if you bend this cable, right, first of all, it's made out of glass, so you might break it. But even if you don't break it, if you bend this cable, it might create an issue with this. What is it? If I bend it, I mean, we got to bend them, right? But if we bend them too much, too sharply, then what's the potential problem with this? Let's bend it. Let's bend it and let's see. What's the potential problem with this? Sorry? Yeah, now we're not above the critical angle. So now we get this going from glass to air, and it refracts instead of reflects. And now we've lost our signal, right? So the downside to it is that you can't turn it too quickly. It's got to have a nice wide sweeping turn in order to not lose that signal. Okay, so this is a fiber optic cable. What if the question said, here's the index of refraction, 1.50. Here's air, where the index of refraction is 1.00. What's the critical angle? This isn't any different than these questions you were solving yesterday, right? It's just context. Now, in all likelihood, on a test, you're going to get a question with context, as opposed to just a word problem like this. But they boil down to exactly the same thing, right? So how would we tackle this? We just say sine theta c is equal to N2 over N1. N2 would be the air, N1 would be the glass, 1.50, and we'd solve for theta c. And I think that works out to be, like 48 degrees or something like that. Make sense? Now, if you were doing research, worked for a company that made fiber optic cables, and you were doing research and materials and whatever, trying to find better materials, you'd try to find a material, ideally, you'd try to find a material here to use for a fiber optic cable that had a lower or a higher index of refraction. What would be the goal? You'd want to have a higher index of refraction, right? If you could. How come?
Because then it has the critical angle is larger. So that
No, critical angle is, right. The critical angle is smaller if you create a higher index of refraction there. Critical angle is smaller, and that creates more possibility of total internal reflection taking place. In other words, if you do bend it somewhere, there's less possibility of that light refracting out. Make sense? All right. Yesterday we moved on from refraction and total internal reflection to another pretty big application of refraction called curved lenses. We said there was two types of curved lenses. There was the convex curved lens, or otherwise known as the converging lens. These are the ones that are thicker in the middle than at the edges. And then we have the diverging lenses, or the concave lenses. These are the ones that are thinner in the middle than they are at the edges. Why do we call these converging? Well, because rays of light that are parallel to the principal axis converge at one point. What do we call that point right there? Yep, the focal point, right. Rays of light down here that are parallel to the principal axis, they don't converge at a focal point, rather they diverge. They're going away from each other. But if we extend them back, we see that they diverge away from a point that we call the focal point, right? Instead of rays coming together at the focal point, down here we have rays going away from each other at what we call the focal point. Now, we do some ray diagrams yesterday on a template that I handed out to you. of some convex or converging lenses. This, we said just a second ago, is called the focal point. This one we'll just call 2F. It's a little spacer. What do we call that point right in the middle of the lens? The optical center, or the OC. This is called the, this line is called the principal axis, yeah, principal axis. And remember that all of those rays that are parallel to that principal axis converge at the focal point. So let's take a look at a couple of these again. Not all of these ray diagrams, but just a couple of them to kind of refresh your memory with it. This time we have our object way out there, okay? It's beyond 2F. If this is 2F, then our object is further than 2F. Now, how much further than 2F? It doesn't matter. The characteristics or the attributes of this image will be the same no matter how far beyond 2F I put it. The size will change a bit, but it'll either be larger, smaller, same size, same as it is close to 2F or really far away from 2F. Let's draw the ray diagram for this one. First ray always goes from the top of the object. Where do I draw it to? First ray goes, yeah, Martin? Parallel to the principal axis, yeah. Now it actually bends when it strikes the lens and then bends when it leaves the lens, but we're just going to draw it straight into the middle of the lens and then we're going to have it bend there. Gives us the same effect. It's just not quite as accurate. It's just a lot easier to draw. Now where does it bend from there? Where does it go? Where does it refract? Yeah? Yeah, it goes down through the focal point, right? Remember, all rays parallel to the principal axis will refract or bend through the focal point. Second ray goes where? Through the optical center. Where does it go from there? Straight through, yeah. It's going to bend a couple times in there, but in the end it has the same effect as going straight through there. My image is formed right here, and that image is going to have three characteristics. What are the characteristics of that image? Number one, doesn't matter what order you give these to me, by the way. Number one is going to be, it's smaller. When you look at that red arrow relative to the black arrow, the red arrow is smaller. The image is smaller than the object is. So we've not magnified it, but we've made it smaller. Two, what's the second one? Harrison? Good. It's either upright or inverted, and this one is inverted. It's upside down. And the third one, this is the hardest one. Well, it's not really the hardest one once you learn it. It's just, when you're first learning it, it's kind of tricky. Okay, this one is Ryan? It's real. Yeah, we say this one is real. What does that mean if it's a real image?
It's solid lines converging.
Solid lines come together, yes. That's how we tell that it's real. But what does it really mean if it's real? Yep.
It can project an image away, separate onto a screen.
Yeah, we can project the image onto a screen. Now, it doesn't mean that we are projecting it onto a screen. Hey, I can stand right here, look through the lens, and see this image right there through the lens. I'm not looking at it through a screen in that case, but I can project it onto a screen. If I take a white piece of paper and put that white piece of paper right there, I'll project the image onto that piece of paper. Make sense? Now, if I take that piece of paper and I move it back here, what am I going to see? The image? I'm going to see a blurry image, right? I wouldn't say that I've projected the image onto a screen because it's not focused. But it's not that there's nothing there. It's just that it's not focused there. Okay? In order to say that we have a real image, we have to be able to project a focused image onto a screen. Okay, let's do another one here. First ray, parallel to the principal axis, and where does it go? Where does it go? Brenda, where does it go? Down through the focal point, good. Second ray, where does that go? Down through the focal point, isn't it? Where does the second one go? Ben? Optical center, keeps going straight through. Find the image is formed over here, and you can see that the characteristics of this one, clearly it is larger, smaller, same size, Dawson. Larger, quite a bit bigger, right? It is right side up or upside down? Yeah, it's upside down, and it's real or virtual. Quinn, is this one real or virtual? Yeah, it's real. We know that it's real because solid lines intersect. That means that we can project it onto a screen if we wanted to. Remember there was no image formed here? Parallel down through the focal point, and then down through the optical center, these rays are parallel to each other. They're never going to intersect, so there's never going to be an image formed. This one, there was an image formed, parallel down through the focal point. This one went down through the optical center. They don't intersect down here anywhere, do they? So what do we got to do with this? This is where we extend the rays with dotted lines. We find that the dotted lines intersect over here. The dotted lines intersect over here. Now, what are the characteristics of this image? Larger, smaller, same size. This image is larger. What else? Right side up or upside down, Maddie? Yep. It's a virtual image. Doesn't matter what order we give him, that we give him to us in, right? It's a virtual image. Which means it cannot be projected onto a screen. I've got to stand over here like this and physically look into the lens in order to see it. It's a virtual image. We know that because it's dotted lines that intersect, right? Okay, what else? Right side up or upside down? Look at the arrow. Caitlin, right side up or upside down? It's upright. So larger, virtual, upright. This is the magnifying glass, right? You want to magnify something, you put your lens close to the object. But you got to make sure that if the focal length of the lens is 10 centimeters, then your object has to be less than 10 centimeters away from your lens. That produces that image that's larger, upright, but you got to look into the lens to see it. Okay? Why would we not use this at a movie theater? Like at a movie theater, we project the image upside down, right? Well, kind of. The object would be upside down. Why would we not use this in a movie theater? Yeah?
You'd have to have a massive lens that it would
Okay, well, exactly. People would have to physically look through the lens to see it. You couldn't project it onto a screen, right? It has a desired effect here. The image is larger. It's upright. That's great that it's upright, but it's virtual. And when it's virtual, you can't project it on a screen, which doesn't make it very practical for a movie theater when everybody has to be kind of crowding around the lens, looking into the lens in order to see it. Right? Notice that whenever we had a real image here, a real image was always upside down. And a virtual image was always, well, there's only one virtual image here. It's always right side up. You're going to see when we draw the ray diagrams for the concave or diverging lenses that those same patterns hold. We're going to make this my focal point. We're going to make this 2F. Principal axis, optical center, same deal as what we had for the last set. First object, way beyond 2F. Well, or just a little bit beyond 2F. It doesn't really matter. First ray, parallel to the principal axis. Where does it go? For the converging, it went down here, right? This one go down here? Down through the focal point on this side? No. This one goes up here, as if it's going away from this focal point. It's diverging away from that focal point. The second ray is going to go down through the optical center just like it did for the converging, and it's going to keep going straight through just like it did for the converging. The image will be formed right here. If you need a ruler, by the way, what are the characteristics of this one? Larger, smaller, same size. Smaller. The image is smaller. Is it right side up or upside down? Upright, right? It's right side up. Is it real or virtual? Solid lines intersect, it's real. Dotted lines intersect, it's virtual. We got a solid and a dotted here, right? Not really, actually. We have two dotted lines, because if we have the extension of that first ray, and if we extend that second ray back, then it ends up being two dotted lines that intersect, and we end up saying it's a virtual image. Now, usually when I draw these, I don't actually draw that second dotted ray back. I just remember, look, okay, if it's one dotted ray, if you see one dotted ray, really there is a second dotted ray, and it's dotted lines intersecting, therefore it's a virtual image. Remember what we noticed the last time? If it was real, it was upside down. If it was virtual, it was right side up, and sure enough, it still is, right? Now, virtual before was bigger. Now virtual is smaller, so we can't look at the size in relation to real or virtual, but we can look at the attitude or the orientation in relation to real or virtual. Let's take a look at the next one. This time we're at 2F. First ray, parallel, diverges away from the focal point. Let's extend that back through the focal point. Second ray is going to go down through the optical center. Keeps going. Look at that. Where's the image formed? Right here. What are the characteristics? Larger, smaller, same size. Nathan? Yep, smaller. Is it upright or inverted? Logan? Yep. And is it real or virtual? Real or virtual, Bruce? It's going to be virtual, yeah. Now, we say virtual when two dotted lines intersect. Really, we have the two dotted lines there, right? We just haven't drawn the extended second ray back. So we don't see the second dotted line, but that's really what it is. Once again, the pattern holds. If it's virtual, it's upright. If it's real, it's inverted. All right, I'm going to ask you guys to draw the last three ray diagrams here yourselves. The reason that I'm asking you to draw the last three on this one, and I didn't on the front side of the page, is because I think you're going to start finding patterns in these ray diagrams pretty quickly. Patterns that didn't exist on the front side. So I think you're going to find that this is easier. But if you have any questions, just let me know as you're working on it. Let's try a little math with this. We've learned to draw our ray diagrams, and if we draw our ray diagrams perfectly to scale, then we can learn a lot from those ray diagrams, including sizes of images and distances. But we can also calculate those numbers and not have to worry so much about doing everything perfectly in our diagrams. There's two equations that we're going to introduce here today that are going to help us out with that. The first one we call the lens equation, or the thin lens equation. Looks like this. 1 over f is equal to 1 over do plus 1 over di. F would be the focal length, which is the distance from the lens to the focal point. Do would be the object distance, the distance from the object to the lens. And di would be the image distance, the distance from the image to the lens. What units do you think we want those in? What units do we usually want to be in? Pardon? Meters. Although for this one, it doesn't actually matter as long as we're consistent. How come? If I use centimeters, why does it not matter? Yeah, it's a ratio, and it ends up canceling out, right? The units end up canceling. I'll suggest to you actually that you're going to end up using centimeters for this more than you use meters, just because it's centimeters that the question usually ends up giving you. If you're more comfortable converting it to meters, then convert it to meters. But as long as you're consistent, it doesn't really matter if you convert or not. Now, the other equation is called the magnification equation. M is equal to HI over HO equals negative DI over DO. This just gives us a number that tells us how big the image is compared to the object. If magnification is 2, then the image is twice as big. If the magnification is 0.5, then the image is half the size of the object. Now we've got a big chart here that we want to fill in that is going to help us out with the signs, positives and negatives, because there's quite a sign convention that goes along with all of these variables. It's not crazy hard, but we do have to be really careful and pay attention to it. Otherwise, can you put a negative here where it's supposed to be positive? or vice versa, then we're going to get the question all wrong. Let's identify, let's first identify when it should be positive, when it should be negative. Those are my two columns. And then down the left side, let's identify when DO should be positive, DI should be positive, and F should be positive, and when they should be negative. We'll fill in the rest of the table in a minute here. DO will be positive when you have a real object, which for us in physics 30 will be always. You will never have a question in physics 30 involving a virtual object. That can happen. It can happen with more advanced problems, but you need a two-lens system in that case. So sometimes the image formed from the first lens can serve as the object for the second lens, and in certain circumstances that can be a virtual object. But you don't have to worry about that in physics 30. So for us, it will always be positive, the object distance. It will be negative if it's a virtual object, which for us in physics 30 will be never. DI will be positive if it's a real image. And it's a real image, well, you saw in some of the ray diagrams it was real and some of them was virtual. You always get a virtual image if you have a diverging lens, but when you have a converging lens, it was real for the first three, and then it was virtual for the last one. So you got to just kind of think of those ray diagrams or redraw those ray diagrams and identify whether it's a real or virtual image and determine whether DI is positive or negative based on that. F, the focal length, is positive if it's a real focal point. And when you have a real focal point? You have a real focal point when you have a converging lens, because that's when the rays really go through the focal point. And it's negative if you have a virtual focal point. And it's virtual if you have a diverging lens. Now, the last two rows in this table relate to HO and HI. HO is positive. Notice I've colored it differently because the pattern is different, right? The blue ones are positive if they're real. They're negative if they're virtual. The green ones are positive if they're upright. If you have an upright object, you have a positive HO. Or if you have an inverted object, you have a negative HO. HO is almost always going to be positive, but it is conceivable that the object could be upside down. HI will be positive if it's an upright image. And it's going to be negative if it's an inverted image, which that happens all the time, right? One thing to remember, though, sometimes it can be very helpful. Remember that pattern we noticed? If it's a real image, it was always upside down. If it was a virtual image, it was always right side up. So even though HI is not, like HI, the positive or negative is based on whether it's right side up or upside down, you can also think of it in terms of real or virtual, right? If it's real, it's going to be upside down, and therefore HI will be negative. If it's virtual, it's going to be right side up, and therefore HI will be positive. One last one that doesn't kind of fit with any of them, so we make it separate. It's magnification. Magnification is positive if the object and image are on the same side of principal axis. And what do I mean by that? Well, if they're both upright, then M is positive. If they're both upside down, then M is positive. Does that make sense? If they're both the same way, M, the magnification is positive. If one is upright and the other is upside down, then the magnification is negative. So you get a magnification that's +2. It means that the image and the object are both either upright or upside down, both of them the same though, and the image is twice as big as the object. You get a magnification that's negative 0.5, then it means that the image is flipped over, and it means that the image is half the size of the object. Let's take a look at this question on page 681 here. It says a 2.5 centimeter high object is placed 10 centimeters from a diverging lens. This is something that I definitely want to circle, diverging, to remind me that it's a negative focal point. Right? Remember diverging lens, negative focal point? It doesn't tell me anything about anything else, but it does tell me that it's a negative focal point. Determine the image distance, the image height, and the attributes. The attributes are just the characteristics here. We're going to say that HO is 2.5 centimeters. We're going to say that DO is 10 centimeters. And we're going to say that the focal length is negative 5.0 centimeters, negative because it's a virtual focal point. It's a diverging lens. We want to determine DI, we want to determine HI, and we want to determine the attributes, which we'll worry about after we calculate those two values. Now, the first thing I'm going to do is say 1 over F is equal to 1 over DO plus 1 over DI. Plug your numbers in, including your signs, before you rearrange. 1 over 10 plus 1 over DI. Now, watch this little trick on my calculator here. How many people feel like they're pretty good with fractions? Yeah, pretty much none of you. I figured so much. I figured as much. Okay? People aren't good with fractions anymore. The good news is your calculator will do it for you. Here's what I'm going to do. 1 over negative 5 is the same as saying negative 5 x to the minus 1. Take the 1 over 10 over by subtracting. So let's subtract 10 x to the minus 1. Make sense? I just said 1 over negative 5 minus 1 over 10 equals. Is that my answer? No, that's 1 over di. To get di, I'm going to go 1 over that, and I end up getting negative 3.33. We finish off HI. This one's easy too. HI over HO equals negative DI over DO. This is my magnification equation. I'm going to say HI over 2.5, because that's my HO, equals negative 3.33. Notice DI is negative, right? So it's negative over DO, which is 10. So all I'm going to do for this is say negative 3.33 divided by 10. I'm going to multiply that whole thing by 2.5, and my image height is 0.83. Now, what does that tell us here? Negative DI tells us that it's a virtual image because it's a negative DI. Positive HI tells us that it's an upright image. And the fact that the object is 2.5 centimeters high and the image is only 0.83 tells us the image is smaller.